Let me introduce our speaker. She is Tanya Triplett from the physics department here at USU. Tanya's been at USU for a long time. She got her undergraduate degree at U of U, came here, got her graduate degree both in physics. She's now on the faculty here where she is, I think it's fair to say, I can ask my boss to confirm, but yeah, fair to say she's one of our most esteemed teachers. She's very well known for her ability to take big science ideas and, well, explain them to the rest of us. And you may know that the theme this year in Science Unwrapped is Powers of 10, where we will be exploring the universe from the point of view of different distance scales, from the very largest things to the very smallest things. And Tanya has been tasked with telling us about the very largest distance scales in the universe. And in particular, she's going to be addressing a very ancient, timeless question, are we alone? So please welcome Tonya Triplett.
Thank you. All right, well, this is my normal classroom, so welcome. As I start a new class, we usually begin with explaining how to get an A. And so that's being the most important thing to you today. I'm going to explain some different math instead. So rather than calculating your scores, since we're working in powers of 10, I need to do a brief math review. So jump on board, all of you people who think that math didn't matter and that you're never going to use it again. We are here to do some. And for those of you who don't know that you're going to say that one time in your future, it's time. You're ready. And we are ready to do some math. And so I don't care how old you are. If you can add, you can do this. So you should have a piece of paper and hopefully something to write with. If you haven't got those, if you raise your hands, I have some people who would help you. So just raise your hand and somebody will come. Okay, so we're going to be doing the math together. And so each time we do some multiplication, you're going to need to write down your answer. And the thing is, I don't know what your number is. That's your job. And you're going to do the math as we go tonight and reach your own answers. So at the end, we'll have a minute and talk about what your answers are. So math review. We're going to be multiplying in powers of 10. And so when you multiply in powers of 10, then it works to just add the powers. So I've got some examples up here. If I multiply 10 to the 4th times 10 to the 7th, then that's 10 to the 4 plus 7, which is 10 to the 11th. 4 plus 7, 11. So if you're ready to multiply, then we can multiply those numbers, and we're going to multiply and divide powers of 10. So if we divide, then we'll have a negative number, and so then we'll subtract. And so if we are going to do that, then we do, like my second example, 10 to the 5th times 10 to the minus 3rd, dividing by 10 to the 3rd, and we just subtract. So 5 minus 3 gives me 10 to the 2. So some pretty basic math, powers of 10. The last one, if they're both negative, then we add negative, but I don't have that one for you, so you should be fine. All right, a couple more hands. Okay, just a few more in this back corner. Do we have anything left? Okay. Okay, so we're going to get started with some math fun. And the question I want to start with is, why are we doing this? And should we search for life? And so this isn't a new question, but it's been phrased in more recent history. And I like the Morrison and Cocconi take on it. The probability of success is difficult to estimate, but if we never search, the chance of success is 0. 0 is an appropriate answer in science. Sometimes 0 is exactly the right answer. But not trying and getting 0 may not be the right answer in science ever. And so we have this big question, are we alone? And so I have taught, that's so strange, I have taught a class called Intelligent Life in the Universe here on campus for many years, and so have appeared in the newspaper, and so it's perhaps possible that there might be life, but just so we understand at the beginning, I don't think that the aliens have arrived. I have not been kidnapped by one. I do not sleep with a tinfoil helmet, and I'm pretty sure that crop circles are a hoax, all right? Because I just can't imagine aliens mastering interstellar travel and coming to graffiti our wheat. So, given that that's the state, I want to do actual science on this same question. And so, we're going to ask the question that SETI asks when we ask, are we alone? And SETI stands for Search for Extraterrestrial Intelligence. They're the group that we're going to be tracking tonight. Now, when we ask really what we're searching for today, NASA has already addressed this question. NASA and our space agencies, ESA and similar, are searching for habitable worlds, a place where life might possibly find a method of survival. That's what we search for, habitable worlds. SETI is searching for technologically advanced life, and that may turn out to be much harder to find. And so we're going to track that one as well. But because NASA has done so much work in this area, we're going to look at where we stand on this today. So we'll start with the Drake equation. This is Frank Drake. He proposed the Drake equation, and this equation asks an underlying question: what are the chances? The number of civilizations in our galaxy who might phone us tonight. All right, so while we're sitting in this room and overnight tonight, how many of those civilizations will dial into Earth and send a message? Now, the answer is an actually complicated one because we expand that over our lifetimes, but we still want to know how many of those civilizations there are. So this is where the math begins. So we're going to do the Drake equation together. And you guys are going to do the multiplication as we go, but I need to tell you we're going to use the one in red, the modified format. The original Drake equation I put in for Frank. But we're going to combine a bunch of terms. And so we'll combine the first three and this one, and then these two, and those two. And we'll get some combined terms into our equation so that we're going to look at 4 terms. All right? So we want to talk about the number of habitable planets. So we'll count our number of civilizations, and it will be the product of, so you guys are going to do the multiplication, the number of habitable planets. So in physics, how we do this. First thing you do in solving a physics problem is you write down the equation. All right, so on your pages, since, well, it's not like everybody got gung-ho and wrote. All right, so on your paper, what you do is you write down the equation, the number of civilizations equals, and then we've got this n with subscripted HP. That's going to be our number of habitable planets. And then we'll multiply that by the next term, f, with a life down below it. And that's the fraction of those planets on which life has arisen. And then we'll talk about the fraction of those planets, so then we'll multiply by the next term, on which a civilization capable of interstellar communication has arisen. And finally, how many of those exist within, well, our light cone, in our time and space, so that they could talk to us now. And so that's what we're going to be doing, and you guys are going to be keeping track of the numbers as we go. All right, so let's get started. NASA has done significant searches for exoplanets. That's the name that NASA uses now for the search for these planets that are around other stars, stars besides our own sun. And of these missions, I'm going to talk about 3. And so we'll get started. We'll start with the number of civilizations equals the number of habitable planets. So that's the first thing we need to calculate, this number of habitable planets. And it has its origin in the Kepler mission. And this Kepler space satellite that was launched took data and has its answer. And let's go ahead and watch that. See if it pulls itself up or if I have to find it twice. Not that one. This one. Okay.
So where do we start to look? In 2009, NASA took a major step in the hunt for life beyond Earth, launching the Kepler Space Telescope to track down signs of Earth-like planets beyond our solar system. Up until then, astronomers had found about 300 exoplanets, but few were anything like Earth. Small, rocky planets like ours are not easy to spot.
Planets are literally lost in the glare of their parent stars. The brightness difference, the contrast between a star like our sun and the Earth that's right next to it is 10 billion to 1.
So instead of hunting for light reflecting off a planet's surface, the telescope focuses on starlight.
What Kepler did was look in a part of the Milky Way galaxy where we had lots of stars in a small field, and it just took pictures over and over again. And occasionally, if those stars have planets, then sometimes those planets would come in front of the star.
As the planet comes around, it's going to block part of the star, and that light won't get to you. And so that constant level that you see from the stars suddenly goes down just a bit.
So these momentary dimmings of light that repeat once every orbit are indicative of a planet orbiting a star.
Astrophysicists like John Asher Johnson and his team at Harvard use Kepler data to estimate an orbiting planet's size and distance from its star.
The dips are pretty deep, so it must be a fairly large planet.
Deep dips in the star's light mean the planet is really big, or the star is really small.
The spacing between this, what is that, like a day or two? A couple
And
days,
frequent dimming means gravity has drawn it close to the star, making the planet really hot.
It's pretty much like a classic hot Jupiter.
A giant broiling ball of gas like this would not be a great spot for life. So the team looks for signals that are more subtle.
Looking at this, it doesn't look like much, but it looks like there is some kind of periodic signal there.
So what do we know? We know this thing is small.
It's blocking out less than 1% of the light that we're receiving.
Something is causing the star to dim ever so slightly and at longer intervals. Could this be a small planet, closer to Earth size? And the distance from its sun suggests temperatures potentially comfortable for life.
This is really interesting. I mean, this is exactly the kind of thing that we're looking for. This could be a rocky planet somewhere near the habitable zone.
Yeah, this is really exciting.
Yeah.
The discoveries coming from Kepler have been astounding. Nearly 3,000 confirmed planets so far.
The Kepler Space Telescope blew open our understanding of planets.
We have found lava worlds. We've got planets that are orbiting not one, but 2 stars. We have found planets that may be covered entirely in liquid water.
And some of these planets are Earth-sized, with temperatures potentially ripe for life.
Kepler allowed us to see the sheer numbers and the absolute commonness of Earth-sized planets throughout the galaxy. And so the chances of us finding life elsewhere, in my view, is very high.
In fact, using the small sample of sky observed by Kepler, astronomers now estimate that there are tens of billions of planets in our galaxy, the same size and temperature as Earth. These planets could have liquid water on their surfaces. Their rocky cores could hold the building blocks of life. And their stars should provide plenty of energy.
So the Kepler data was collected by looking at a very small section of the sky and looking for what we think of as eclipses. These are times when a planet passes in front of a star. It's called a transit. And if you watched just over a year ago, how many of you saw the eclipse? Because I'm just saying that those are pretty rare, and we had to find those in space. around other stars, which makes it somewhat unusual to find them. And knowing that tells us that if we find many of them, that there are very many, many planets. Our numbers today, if we count G-class stars, which are stars like our sun, would be on the order of 10 billion. If we are willing to accept slightly cooler stars, which we have no reason to think won't work, then we're on the order of 100 billion planets in our galaxy that could support life. 100 billion. All right, so math, that means our first term is 10 to the 11th. So that underneath NHP, you write 10 to the 11th. And so when you're doing it on your page, you write, under your number of civilizations, you write equals 10 to the 11th times, and then we'll get our next number. Now, is that a lot? 100 billion. It helps to take this into perspective. Our galaxy has about 100 billion stars. That means when you look up to the night sky tonight and you look at any star, that star is likely home to a habitable world. In fact, what we conclude from this data is that habitable worlds aren't rare at all. They're common, and that there ought to be one for essentially every star. And in the past, we would have concluded that we were incredibly rare on our planet, but we can't do that with Kepler data now. Now, this gives us a good calculation, a good estimate, and our numbers are good, but it didn't answer a sort of more pressing question, and that is, are those worlds nearby? And the Kepler data is a statistical count, not an actual count. It didn't tell us, look at this world. We got a few of those, a couple thousand. We got a few of those, but our near neighborhood in the galaxy, we don't know the answer to that. And so we have launched the TESS, which is the Transiting Exoplanet Survey Satellite, which is on its way right now. It's executing its orbital location, and it will soon be returning data on planets in our near orbital neighborhood.
Since the dawn of time, mankind has sought an answer to an undying question. Are we alone? Now, humans possess the technology to solve this mystery, and we will shift their gaze to the stars. This is the search for exoplanets. This is TESS.
This TESS is actually going to look for these nearby worlds, and it is beginning its orbit. Now, this is not a new question. It's something that we're already thinking about. And so we're on our way to answer this question even better. Where are those worlds nearby? And so we're ready to start that question next. And this entire sky picture that we're taking with TESS should tell us which planets and which stars to focus our research on. After that, we're ready to start, well, an even bigger question. Which one of those worlds might have life, and which of them might be interested in having some interaction with us? And so we'll have to ask those questions still. But we can't begin to ask those questions until we find out where to search. And that has been what NASA has been working on. Now, let's do the next one. Let's look at the next term in your equation, because we need to be able to talk about all of them. And so this term, this fraction of habitable planets that actually have life, Do you know, of all those habitable worlds out there, how many of them will have life? And really this asks a question of us, is life easy or is it hard? Does life arise on every world, or are we the only world that ever had the start of life? Is it so hard that it'll never be anywhere else? Or should we expect to find it every place we look to? Life, how common is it? And so we need to answer this question, and the way we're going to answer it is numerically. So I'll help you, and we're going to choose a number for this. So if you think that life is easy, and therefore that life everywhere should exist, then for the fraction of habitable planets you might choose 1. Just a minute, we'll talk about possibilities. So if we look at life on Earth, for example, this is Grand Prismatic Spring in Yellowstone, and those colors, that's life. That's cyanobacteria. And here we have life that's showing up in some pretty inhospitable places. It's not a place where you and I could live. On Antarctica, we have life in the Red Falls, and this is microbial life. And could you then, on a world that's very hot or very cold, have life occur? It works at Yellowstone, it works at Antarctica. Could it work if that world was colder than ours, if it was warmer than ours? We think so. What if it's more like ours, and it's green everywhere we look, and you have your beautiful island and all the surrounding seas that are full of life? Or maybe it'll be life closer to home. You could find some in the cities, or maybe you out in the country club. Is life easy or is it hard? And so many scientists today argue that life is easy. But I want to ask that question again. Is life easy? That's not what I wanted. Perhaps no. And I want to look at this the other way. On our planet, we're getting so much better at searching. We've sent probes to many of the surfaces of worlds in our own solar system, and we've been back to Mars many times. And we have yet to, well, be taken to their leader. We haven't found microbial life in all of our experiments, and we've tried. And for all of our searching today in our solar system, the answer is no. And so does that mean that in our solar system only Earth works, but in other systems Earth-like planets would work? We don't know. We don't know the answer to this question. And so despite all our searching, we have found one world with life, and it's ours. And if you think that we're the only one who is going to have life, then a low answer on this could be 10 to the minus 11th. So that would be 1 out of the 100 million in our galaxy if we're the only one. So that's 10 to the minus 11th. But I don't know what your answer is. You need to find yourself somewhere between 1 and 10 to the minus 11th, which is really small. Do you think that life is pretty common? Maybe you want to go 10 to the minus 2, 1 out of 100. Do you think it's 1 out of 1,000? That's 10 to the minus 3. Is it 1 out of 1,000,000? 10 to the minus 6th. Is it really 1 out of 100 billion? 10 to the minus 11th. All right, so write down your answer, because I don't know what your answer is. At this point, you do something with your paper. All right. So your answer, you should all have 10 to the, oops, hang on. You should all have the first number 10 to the 11th, but this next number, this one's the one you get to choose, the first choice. So put something. I don't know what the answer is, but here's the best news. Your guess is as good as NASA's. So we're ready. Put your answer in. Okay, now the James Webb Telescope is in the planning stages and getting ready to be launched. And James Webb will be able to look at the atmospheres. Here we go. Webb. Oh, that's going to be a problem. All right. The James Webb Telescope is going to be able to look at the atmospheres of nearby worlds. Specifically, we're hoping to look at the TRAPPIST-1 system. This is only 40 light years away, and it has lots of worlds. And we'd like to look at the atmospheres of those worlds, because there is an element that if we find it in the atmosphere is a dead giveaway for life. And it's, do you know what it is? It's not carbon. Carbon is common in the universe. What is it? Go ahead. Nope, I would like to find water, but that's not the one I'm going to search for. What? Oxygen, you're right. Oxygen is that gas that we're going to look for. Now, I would look for it in various forms. I'd take it in the O2 that we breathe, but I'd also accept it in O3, ozone. Because there isn't a method of building those gases that we know of in an atmosphere except life. If there's no photosynthesis, then we don't know how to get that in an atmosphere. And James Webb Telescope is designed to look for oxygen in the atmosphere. That's what we're searching for. And so we're on the verge of being able to answer this question too. Well, we could look at the atmosphere of a planet. And so that will be our next step. And we're excited to find out. All right, we're ready for the next term. Keep doing your math, you're doing great. All right, so the next one is the fraction of life-bearing planets on which a civilization capable of interstellar communication has at some time arisen. Can the aliens use a radio? All right, now more specifically a radio telescope. But this is the question. Can they do it? Because I need them to send a message, and we're listening in radio, so can they talk in radio? Well, think about what has to take place for that. If they're going to be able to speak in radio, then at some point, single-celled life will have to become multiple-celled life. And at some point, that multiple-celled life will have to get out of the ocean so that it can, well, live on the land and eventually build a laboratory and use its hands to build a telescope. We don't know if that's going to happen or not. That's a hard question to answer. But we could talk about, well, whether to think of this as a big number or a small number. So I want to look at whether we should think about this as large or small. So taking it from the small side, I just have to note that after over 4 billion years of planetary formation and having life on our planet, we mastered this skill in the last century. Just saying. Your great-grandparents would not have qualified as intelligent life for SETI because they couldn't operate a radio telescope. Now, to be fair, you may not qualify either if you can't operate a radio telescope. Just checking. All right. But can our civilization do this? And this is a hard question. It took us 4 billion years to get here. So will it take everybody 4 billion years? It might. Were we remarkably fast? 4 billion years, you know, it took us, and maybe their lifespan of their star at a mere 10 billion years won't be long enough? It's a possibility. What if we were really slow? All right? What if we were, you know, slower than average? Then other worlds would be able to do those evolutionary tasks faster, and they could arise at this place sooner. And if that was the case, then we'd expect this number to be smaller. Now, be careful of how you analyze that. Think carefully. The answer here is if you think we're really smart and fast learners and quick evolvers, then you have to choose a low number. If you think that we're a little bit on the slow side, and everybody else can do it better than we can, and we are the slow people of the universe, then you can choose a higher number. But if we just play around with this, doing just time on our planet gives us a number of about 5 times 10 to the minus 8th. Now, I don't know, like 5 times 10 to the minus 8th. Or we could take this another way, and we could look at the idea that life is older on at least half of the stars of our galaxy. We're middle-aged, and that means there's younger stars, but there are older ones too. So shouldn't half of all those stars be older than we are? So if we're just average, then my number should be half. I don't know. We'll get some more data. Here we go. All right. So what if you want to go with the low number? So choosing a really small number like 10 to the minus 8th. All right. Well, is it hard to get a technologically adept civilization? Maybe life is really common, but it always stays single-celled and in the ocean. And stars come and go, and single-celled life lives in the ocean. Maybe it even figures out multiple-cell life. But what if there are no continents? I mean, how will that work? If you have a water world, you can't build a laboratory. Yes? Maybe they're mermaids. This is possible. And so we impose our own problems on other civilizations, and that may not be fair, but can you build a radio telescope? It's really hard to do experiments with electricity underwater. Just saying. All right. So if that's the kind of life that is common, but technologically adept life, like us, might still be uncommon. There's not really a reason to argue that all life should be like us. Maybe. So let's go the other way. All right, let's go with a higher number. Suppose we want to argue that intelligence is common and we should find it everywhere. Well, let's just look at life on our planet. In its amazing diversity, there is many, many life forms on our planet that are intelligent. I chose some fun examples. Fortunately, I had a last moment and included people. It's just a fraction. But what we argue to be pretty intelligent species on our planet. And so if you just want to be intelligent, then maybe this is common. In fact, evolution would argue for this. We call it convergent evolution. In this case, what we talk about is that if there is an ecological niche, then life that live within it will grow together, grow similarities, because they fill that niche, whatever that is. And so if we look at dolphins and sharks and killer whales and tuna, these did not have the same origins. They, some mammals and some fishes, and they don't have the same origins in their evolutionary history, but they look the same. And they look the same because being torpedo-shaped makes you a really fast swimmer. And really fast swimmers get to eat better. And they do well because of that, and really fast swimmers get eaten less often. And that means if you don't become food for other things, or you don't, and other things are your food, then you tend to flourish in your ecosystem. So maybe this is a good idea. It works for fishes in our ocean. Other things that we see, it has been very handy for life to figure out how to see. The advent of an eye, something that can take light and turn it into useful information, use it as one of our senses, we find in all kinds of living things. And they don't look the same because they don't have the same evolutionary history. But it is sure handy to see. It helps you, well, hunt better and be not eaten better, more likely to survive. And so having eyes has been a really handy thing. But when we look at crabs, maybe being shaped like that is handy. I can't work this one out in my head. We know they have different ecological origins, but why they would want to look like that. Okay, anyway, maybe being intelligent is just as useful. What if being smart is the answer? And it doesn't matter what your shape is. What if being smart is the answer? Then I would argue that this chance that life on other worlds should also become intelligent. So, what do you think? I need you to fill in a number. Now, you can go as high as 1/2. That's 5 times 10 to the minus 1. Okay, 10 to the minus 1 is your biggest number you can have, but you could go as low as 10 to the minus 8th, because we do have to conclude that we live here. All right? So your answer needs to be somewhere between 10 to the minus 8th and 10 to the minus 1. And I don't know what it is, but here's the answer. Pay attention to what it means. If you're closer to 1, then you think that life will be smart, that it will be intelligent and will rise to civilizations on other worlds, and that will be common. If you think that's not true, then you want to go more towards 8. And if you think we're the only ones, the only life in our galaxy, then you conclude 5 times 10 to the minus 8th. All right? But your number needs to be somewhere in the middle, or at one end or the other. You have to choose. So write one down. I'll wait for you. Okay, so have you got it written down? Have you chosen a number? Because we have to move on. I have one more. So the last term is the fraction of habitable planets, or civilization planets that exist and are transmitting right now, compensated for distance. Here's the thing on this one. This all depends on one question, and that is, how long does a civilization last? So we have been capable of doing this since the end of World War II. Now, some of you may have grandparents or great-grandparents who fought in that war, and we have been capable of this since the end of World War II. And that's not very long. So give us about 60-ish years here. And what if the world ends tomorrow? This is a possibility. Okay, so what if our civilization crashes and burns like, well, choose your favorite ancient civilization. Do you like the Parthenon? Because that civilization's gone. Do you think maybe we should all gather in a Colosseum in Rome? Because that civilization is gone. And maybe civilizations don't last very long. Or maybe they do. Because maybe those were the build-up to our own civilization today. And I don't know the answer to that. This is a question for sociology, and I know nothing. All right? We don't do that stuff in physics, because then you have to think about it. All right. But maybe you're more optimistic about this, and you think that the city of the future is going to happen, and 500 million years from now, we will still be living on our world. What if they last for 1 billion years? Excuse me. So your answer, you need one more term. So I need you to choose a value between 5 times 10 to, that's a minus 9, 5 times 10 to the minus 9th, or 1 over 10 would work if you think civilizations will last for billions of years. So that's 10 to the minus 1. And so your term here, 5 times 10 to the minus 9th, or 10 to the minus 1, but you need to be somewhere between. So if you think civilizations are going to last billions of years, then push your answer towards 10 to the minus 1. If you think that they're, well, really, we are capable of destroying ourselves tonight, you know. If you think that the civilization is going to end now, or that we will follow in the paths of so many ancient civilizations, then you need to choose a number closer to 5 times 10 to the minus 8th. All right, you're ready to do the math. Okay, so now we're ready to crunch the numbers. So here's how you do it. You take your numbers, you have 4, and we're just going to take their powers of 10 and add those numbers up. If they're negative, you're going to subtract. If they're positive, you're going to add. Parents, you help with basic math. You're set. You can do this. Break out your phone calculators. Okay, are you ready? I want to show you some math possibilities. So when you're doing your math, you should have an answer now that says, well, no matter what, your first number should be 5. So 5 times 10 to the, well, 10 to the 9th is the biggest number you can get out of all those numbers. And if you had chosen the low number every time, then 10 to the minus 20th is as low as it can go. So we don't know what the right answer is. But you all have done the calculation. And you know what it is now. We can do powers of 10. Ultimately, this equation frames an important question in science. How do we search for life? What are we looking for? How should we do this? And yet, we don't know the terms. We've got one sorted down, and we're still working on it, but we don't know any of the terms. And so we don't have an answer for it yet. But it says something about you. The biggest decider in this equation turns out to be that lifetime of civilizations. Mathematically, it's the biggest player because the others tend to cancel each other out. Which means that, well, this asks who we are. What is life? Are we self-destructive? And so life is going to end soon? Low number. Are we, well, do we build? Are we those good representatives of life? Because, well, since we don't know the answer, we get to choose it ourselves. And if you're proud of your answer, I want you to take your paper and write your name on it. And you can leave them with me and we'll tally them up and we'll put them up on the website so you can see what the average was and what our numbers came out to be. So I know you did great math. We won't check your math, don't worry. All right, but you can leave those with us tonight. But what I want to do is offer you some time to answer questions. And so this is the end of my prepared presentation. Okay, so I'll take questions. We have a few minutes. Yes, first.
So my question is about the Kepler. So for the eclipse to happen, the planets have to pass right in front of the sun, facing us, right? So do we know if star systems tend to face us that way, like do they orbit around their sun?
Okay, so what about this Kepler data, and do we end up with many of those planets passing between us and the sun? It turns out that it has to be on exactly the right angle, right? And we know that too. And there is no preferential angle. So because of that, that's how we do our calculation. We say for all of the ones that we found, we should have missed that many more that can't accomplish that same task. And that goes into the statistical answer from Kepler, all right, which is different than the number of planets we found, which is on the order of about 3,000. Okay? All right, your question's next. Yes. Oh, this is so sad, because I hope you believe it's not true too. Because while it is possible, I don't think it's true either. Did you put that low number on yours for your sad answer that we could get destroyed right now? Me neither. But that's how we would determine that answer. Okay, back here.
Okay, so do you believe in the theory that the dinosaurs, how they were the original inhabitants of the Earth and we were the aliens that crashed down to the Earth that was the meteor that destroyed the dinosaurs?
Wow, this is an excellent conspiracy. Probably, I want to say, without repeating the entire conspiracy, that there are many that somehow conclude that life as we are today did not arise from the first life on our planet. And there is not a missing link in biology. We are related to the very oldest forms of life on our planet. We are life on our planet, not the aliens. Yes? So I think you're asking about the Kepler data and whether we're pursuing those planets. Well, because we know that we have planets there, of course, there is a group of scientists who are going to continue to study those specific worlds. But we don't have plans to launch another telescope to look specifically at them again. So we don't currently have those plans. Clear in the back. Yes? Right, and your question about from the perspective of looking at these values, it's fine to talk about our life and all these worlds, but will life emerge? And that's that term of the fraction of those habitable worlds that will have life arrive at some time arise on them, and we don't know. Just to note that we have never reproduced this in a laboratory on Earth. And so it may be so difficult that we are the only ones in the universe. And that term may be the answer. But we don't know. We haven't found any other life yet, although that would be one of the most exciting discoveries of all time. So I hope so. Clear in the back. Oh, how will we know if we discover oxygen in a planetary atmosphere? The James Webb Telescope is set up with a diffraction grading system that will be looking for specific elements in the atmosphere. And we can do that with some pretty basic chemistry and telescopes. So we're going to be able to know that answer. And James Webb is equipped to ask it. Over here. Yes, please. How was the Drake equation derived? Frank Drake, when he asked the question, he asked all of the possible problems that could, right? And he looked at all the things that could determine whether or not life could be there. It's not really derived, more made up is a better way to look at it. It asks some hard questions, and then we're left to try to decide what to do with it, because we don't know the answer, right? Yours is next. Okay, so where was Kepler looking? Kepler chose a very tiny spot and looked at it over and over and over again. And so because of that, it sees stars that are nearby and stars quite distant within the galaxy, because it always looks on one line. So we don't distinguish. We know where they are, but Kepler did not specifically look for near or far. So just in that spot that it could see. All right, your question's next.
If we make first contact, should we be
If we make first contact, should we be careful of aliens? Probably. I don't know. If you were the alien and you wanted to go visit another world, would you be willing to be a good alien? Or will we be traveling and be, well, the ones that are in the movies, you know, where they land because they come to take over our world and shoot us all? I don't know. I hope they're nice. I would be. Your question next. How long have we been looking for habitable worlds? Or which question? We've been searching for habitable worlds for a really long time. We found the first one in 1992. And since then we have over 3,000 of them today that we know about, of worlds around other planets. But our list of habitable worlds is pretty small. It's still around 30 that we found with Kepler. So a short list, but we've been looking a long time. Clear in the back. Oh, this is a good question. What about other galaxies? So the Drake equation looks in our own galaxy and not in other galaxies at all. There's two reasons for this. We don't look at other galaxies because the radio signals weaken over distance. So they're so far away that we probably couldn't receive their message anyway. But also, they are so far away that the time to send and receive a message could exceed our lifespan of the people on our planet. And so if we're going to look 100 million light years away, then we would have to listen for 100 million years to send a message back. And so our search is in our own galaxy, but we expect that that number should be the same for every other galaxy, and there are on the order of 100 billion other galaxies. And we're just searching our own. Okay, I need to wrap up. Our time is up. If you have questions, I'll still take them when we're done, but I need to excuse everybody so that you can go and do your experiments, and I'll excuse all the student staff.